Well, student, last class we are discussing on linear antennas. As you know, the gain of the antenna goes on increasing as you go on increasing the length of the antennas. So, like that in that discussion, if you remember, I had told you that if you have an antenna of lambda by 4 length and you are having another antenna of lambda by 2 length and another antenna which is of length lambda, and all three are operating in the same frequency, then you will see that the gain of the lambda antenna, the antenna having the length of lambda, will be higher than other two. So, it is a practice that as the length increases, the gain or the directivity both increases. But there is a limitation in this particular discussion. You cannot go on increasing the length infinitely. Once you start increasing the length beyond a length of lambda, then the linear antenna, they lose their characteristics. For example, the dipole antenna which is having a radiation pattern of figure of 8, as you go on increasing the length, let us say for example, for a lambda by 4 antenna, this is a pattern. When we make it lambda by 2, the pattern will be slightly more directional. When we are going for lambda, this pattern again will be further directional. So, this shows that the directivity is increasing, gain is increasing as the length is increasing. But once we increase the length greater than lambda, you will find that the dipole will lose its characteristics, then you will have a pattern like this. A flower type of pattern will be obtained. So, that is why this approach of increasing the length has a limitation, and when you look for a requirement of antenna for very high directive gain, then you cannot adopt this particular approach. So, to supplement this, there is another way of achieving the high directivity gain, that is called antenna array. So, basically antenna array is a process of placing many antennas together in a proper spacing, proper phasing, so that the individual radiations will meet the point of interest in a constructive way, and in other direction they will cancel each other, so that you will get a very high directional pattern in the desired direction without getting anything in the other directions. So, if you look into this definition of antenna array, this is several individual elements or the antenna so spaced and phased that their individual contribution, each antenna will contribute to the point of observation or the point of interest, and all these contribution will get added up there, and it is just the constructive interference approach. So, the net field will be addition of all these individual contribution, then you will get a very strong field at the point of observation. At the same time, they will try to cancel in the unwanted direction, the field will try to get cancelled in the unwanted direction. So, you will not get other pattern in the other direction. Okay. So, when you frame or form a new antenna with many such antennas together with a proper electrical spacing and phasing, then you make a new antenna which is called antenna array. Now, let us look into this particular situation. This is individual antennas. I am showing you here 4 patches. This is a microstrip antenna. This is one microstrip antenna. This is another microstrip. This is another, like that. There are 4 antennas put in one place, and these connections which you are seeing, these are the feeding networks which is exciting these individual antennas, and once these antennas are excited, each antenna will have certain contribution at the point of interest. So, the net field is the addition of this total 4 contribution. So, you will get a pattern. Here actually I have given the pattern which is varying in different directions. So, we will utilize this slide in other discussions. So, that is why I made a common slides like this. But basic idea is that here you are not dealing with single antenna, you are dealing with many antennas. For example, this case 4 antennas, and the net field or the radiation pattern which you are seeing here, this radiation pattern is the contribution of these 4 elements or the antennas. Here do not get confused with so many such multiple patterns, because this particular slide is to tell you how phase array works. So, that is why multiple patterns I have brought into this thing. Otherwise, you will be getting a pattern like this, that when you will be utilizing 4 elements, then in your desired direction, let the direction is this, you will be getting a radiation pattern, and other direction theoretically you are supposed to get null, no radiation, they should cancel each other. But it is not the case in the practical scenario. Reason being is that there will be some radiation not fully getting cancelled, responsible for giving you some minor lobes. This may be side lobes, this may be back lobes. So, ideally an antenna array should give you the maximum radiation in the desired direction, no radiation in the unwanted direction, but practically you will come across along with the major lobe some minor lobes, because zero cancellation, complete cancellation is not possible. Now, the question comes, why do we need this type of structure where multiple antenna systems we are going to put? This is very clear. Single antenna structure, already I have told you in terms of the dipole, if you see the single antenna structure, the gain is not that very large. When you are using single antenna as your radiator or single element as your radiator, the gain is not very large. Secondly, the beam width is quite broad. The beam width will be quite broad, like this, you will be getting a broad beam width like this. In microstrip antenna like half hemisphere, you will get a broad beam width like this. But your interest is to create a directional pattern, very highly directional pattern. At the same time, gain has to be enhanced, which is a requirement, which are the requirement for long distance communication, like radar communication, terrestrial communication. If you are looking for those type of long distance communication, you cannot achieve the required gain and the beam width required using single antenna. So, there is a mandatory requirement for the antenna array. That is why for any long distance communication where it is a requirement of high gain and directional patterns, you are supposed to go for antenna array only. Individual antenna will not satisfy that condition. Now, what is the principle? How does it really works? When you look into the principle of the antenna array working, the total field of the array is contribution of each individual field, and the interference is a constructive interference at the point of interest, and it is supposed to be fully destructive interference at the point of not of your interest. Alright. So, the principle is nothing but adding of the field at the point of interest, cancelling the field at the point of not required. As I already told you, practically you will have some side lobes as well as back lobe, because it is not fully possible to cancel the total signal in unwanted direction. Okay. So, that is why, but like in single antenna also you will have a main lobe, like we discussed in your class, you will have a main lobe, along with that you will have also side lobes. So, maybe individual antenna, if I discuss like this, This may be a scenario for the individual antenna. When I go for the array, it may be like this. Very less side lobes, but very large main lobe, directional main lobe. So, it is very clear that we will definitely have certain amount of side lobe or the back lobe, but it will be considerably reduced compared to the single element or the single antenna. Now, when you are going to bring all these many elements together, then it is you just cannot bring like that and connect one after another and get the radiation. It has to be with a proper controlling theories which controls the total performance of the array. So, here in this slide we will discuss what are the controlling factors for array performance. Ultimately, the directive gain, the radiation pattern, the polarization, the orientation of the beam, how these parameters of the antenna array are controlled, how the antenna array are named. So, if you look, the controlling parameters are the geometrical configuration. We start with the first is the geometrical configuration. If your elements are placed in a straight line, for example, like this, element 1, element 2, element 3, element 4, 5, like that, you are placing the antenna like this. So, this is a linear array. So, generally or usually it is considered that in a linear array the elements are equally spaced. It is, if you are talking about a uniform antenna array, which I will be discussing later on, identical elements equally spaced placed along a straight line will create a linear array. Similarly, you can put it in a plane. The array number of elements can be put in a plane, like this is, let us say, x, this is y, this is z, then you have a xy plane. So, now I will go on putting the antennas like this, then you have a antenna distribution not in a line, but in a plane, then it becomes a planar array. Similarly, you have a triangular antenna array, because it is a triangular distribution, you will have spherical distribution of the antennas array, spherical antenna array, circular antenna arrays. So, depending on the geometry you are adopting for a particular applications and the shape of the placement of the antenna element in that particular geometry, you will name your antenna array accordingly. So, it may be linear, it may be planar, it may be circular, it may be spherical, it may be triangular. One of the things which I would like to bring to your notice, triangular array, they occupy less space compared to rectangular array. Your triangular structures, they occupy less space. So, that is why when space is a constraint, generally people they prefer the triangular type of applications, but again you have to compromise with the radiation patterns, the direction, all those things. If it is within your acceptable limit, space is a constraint, maybe you can prefer the triangular array. Then the second term is the, what is the relative spacing. Remember one thing, the very first day of the antenna class I had told you, when we talk any distance term in antenna, whether it is length, whether it is a separation, except the radial distance, all other terms are generally in terms of the wavelength, that the frequency at which you are operating and what is the corresponding wavelength, based on this you will define. Even the radial distance, when you classify this as a far field, radiating near field, radiating reactive near field, there also it is a classification based on lambda, that greater than this lambda by this is a far field, greater than this is a radiating near field, like that we have classified. So, basically the in antenna, when we talk about the space, length, all those things, we talk in terms of the wavelength. So, in this case also, when we are talking about a antenna array, there is a separation between these elements. Each element has a perfect length. Let me just come to this slide, maybe I will show you this. Look here, this is a linear array, 4 elements are placed in a straight line. Each element is of length L. Each element is of length L. It may be lambda by 2 antenna, it may be lambda by 4 antenna, it may be a lambda antenna. Each individual antenna will not exceed in their length more than lambda, because otherwise they will lose the characteristics of individual elements. So, that is why each individual element cannot be greater than lambda, that you keep in your mind. So, but L can be L lambda by 2, lambda by 4 can be lambda. Then comes the separation between these two. So, this separation plays an important role for controlling the field at the point of observation. Reason being, as you know, when you are trying to find out the total field is calculated at the point of observation. Let us say this is the axis which you are telling the array axis or center point of the array, like this is, from this you are trying to go to the observation point from the center point, let us say. Then as your observer is looking to the array, the net field is created at the point of interest, that is the P. Alright. Now I am having array, this place a different distance, this is a different distance, this is a different distance, this is a different distance. So, they are travelling the signal from each individual elements, they are travelling different path. So, there will be a phase because of the path, which will write as 2 pi by lambda into the path. So, this phase, this path difference which is leading, this will lead to a phase difference between the individual elements. But you have to create a situation of constructive interference there. So, if you are looking for a space between the element in such a way that it is giving a phase difference of pi by 2 between two individual elements, instead of adding at the point of interest, they will cancel each other. So, that is why obviously the space between two elements is a very important terminology, important factor which decides how the fields which are meeting at the point of interest P are going to be added up. Okay. So, here you will find two type of phase variation. One is phase due to the travel distance, because of the path which the signal is travelling from the radiator to the point of observation. Another is your excitation phase, when you are feeding the antenna with different current, there may be this each individual element may be fed in same phase source, maybe a progressive phase shift of beta to beta, like that you will proceed. So, you will have a phase variation due to the excitation source, also a phase variation due to the path travel. So, what we are talking is because of the path travel. So, that is why the space between two elements or the space between the antennas in an array is an important controlling factor, which ultimately decides what will be the phase at that point of interest, and that has to be played so that you will have a constructive interference in that required direction. Okay. Next is your excitation amplitude of the individual element. Current element, yesterday class we discussed I0 L. So, if the amplitude increases, obviously the field strength, field intensity will go on increasing, power density will go on increasing, radiation intensity will go on increasing at the point of interest. So, amplitude definitely plays an important role. So, the amplitude of excitation, like 2 volt you are applying, another is applying 4 volt to the same antenna structure, obviously his performance will be better than you in terms of the directive gain, in terms of reaching to the longer distance. So, that is why next term is, which is important, which controls the antenna directional characteristics as well as the directive gain and the other parameters of the antenna array, is your amplitude of the excitation. Then the phase of excitation. Now, you are feeding. So, the feed current is having an amplitude as well as phase. So, that phase of excitation also plays very important role. So, like due to the path travel, let us say they are meeting with a phase of, they are going out of phase by let us say 60 degree. Through your source you can control that, so that you can bring both the antenna to a in phase situation. So, there will be a constructive interference there. Alright. So, that is why the excitation phase and the distance between the antenna, they are basically played before the final design is accepted. So, once the final design is done, your spacing between the antennas remains fixed, because already you have fabricated the antenna. Then what is left in your hand is the excitation phase. So, that you have to go on changing if there is a drift or there is a shift in the radiation pattern at the point of interest. If it is just shifting, maybe because of some atmospheric condition, because of certain variation, or one of the element in the antenna is now faulty. So, the net phase which was calculated based on the separation between the antennas elements are disturbed. So, to compensate that, the things which is within your control is the phase of the excitation. So, you have to play with that phase of the excitation to get the things done. In fact, like ground station array, when we talk about like radar is using antenna array, and you are in the ground station radar you are talking, and it is very difficult. Even if an element is failing, it is not that difficult to handle, because it is within your approachable distance and you can handle, and you can find out which one is a defective element and try to rectify, bring certain rectification with that. In satellite type of application, as you know, it has an inbuilt control system. So, the control systems, when a element fails or a double, triple or multi elements fails, they take care of that, and they go on readjusting adaptive way, so that the lobe which is supposed to come to Chandigarh stays at Chandigarh, does not shift to the other place. Otherwise, as the phase changes, you will see that the lobe will get changed. So, they go on controlling that way. That is the inbuilt satellite control system. But when there is major failure, when the major failure occurs, then really it is a problematic situation, because the control system also fails that way. So, when the control system fails, you are not in a position to know which element has failed. You are not in a position to control the phase through the control system to bring the lobe to your required direction. So, in a worst condition like this, you have to depend on the ground station, and ground station has to take care in certain extent to bring back your lobe to the original position. So, lot of activities, actually lot of good papers are there now to control the faulty element of antenna array in a satellite spaceborne antenna array from the ground station. Like soft computing approach is one of this. In soft computing approach is one of this, where from ground station comparing the received power after the faulty element fault occurs in the antenna array, after comparing that with the original one. Before sending, you are just taking a database of the each element, their placement, everything. Once it is failing there after being launched, then you will be getting a received signal that will be different from what you have kept in your database. When it compares, then the transformation coordinates are searched, then particular location is found, yes, because of this antenna element. Maybe the 50th element, the 49th element has failed, because of which this much of variation is taking place, because already a database for comparison is available. So, that is the way people are